Hello, everyone. Thank you, Emmanuel, for introducing me. I'm very exciting in this conference to share what I have been working on using SIMBA simulation platform to design and validate the high efficiency isolated dual active bridge converter. In the beginning, I will start with introduction, then about what about Revo Drive company, our company. Then I will go to the bidirectional dual active bridge, isolated bidirectional dual active bridge, and then I will concentrate more on the triple phase shift modulation and closed loop evaluation. And then the definition of the triple phase boundary conditions and the triple phase optimizer. Then I will go through the conducting and switching losses and dual active bridge efficiency evaluation. Let me start with Revo Drive. Revo Drive company. Revo Drive company is a leading manufacturer and development service provider of power electronic components for electromobility. Our pioneer technology helped in the certification and hybridization of commercial vehicles and mobile machinery. With around more than 120 employee, 40 in the research and development area. The location is the headquarters is in Pollingen in Germany, and we have a branch in India. The company is shared with another company, Brittle company and Kalyani company in India, 50%, 50%. We have certified for ISO 901 and ISO 5001. Our production is Revo, the drive solution. I mean, for the motor drives, we are providing devices with a different power level from low power level 15 kilowatt or 17 kVA to 320 kVA with a single inverter or dual inverter where you can drive two motors or one motor. And we have also a charging technology where we are producing onboard charger, and now we are working on dual active bridge, which is going to use in battery charging, and we are producing also a battery charging station. Also, we are producing a cabinet drive solution for the Statler carrier or for the crane in the port. So we are providing all the cabinet, which is including over different devices inside, like a DC, like genset, motor drives, and holding the weight in the crane. Bidirectional dual active bridge. What is bidirectional dual active bridge and its application? As you can see here on the picture, it's just a DC-DC converter isolated with the high frequency transformer, where the input voltage and output voltage can be selected. Either depends on the application. So you can put in the one side the battery, and the other side for example, fuel cell. For example, for our application and for our customer now, we have a fuel cell in the primary side with around 120 to 450 volts, and on the other side a battery with the voltage requirement was 600 to 850. This bidirectional dual active bridge shall work in both direction for charging as discharging. The challenging is that we have to get the maximum power of 30 kilowatt in a single stage, and which has the ability also to work in parallel application, for example, with 3 in parallel to get around 90 kilowatt. So the challenges in our side are the high power level. in the dual active bridge, even if you search in the literature on the application, you will find that most of the application of the dual active bridge is working in low level power with some watt till 1, 2, 3 kilowatt, but with a high power level over than 30 or more than 30 kilowatt, it's not too much in the application, in the field of the application. These isolated converter design also more efficiency, which is higher than 98 in a wide range. This is one of the biggest challenges that we are facing. High switching frequency transformer, 100 kilohertz till also 200 kilohertz. The parasitic effect that we are also facing which is the interaction between the parasitic inductors and capacitors in the high frequency transformer with the switching pattern. So we get some too many ringing that we have to damp it, and we have to eliminate it to avoid any unexpected operating for the device. The contribution are the high power density isolated device in single or in a parallel usage, parallel application. And we are providing a 3D calling system because we are running at high frequency switching, high power. So the challenging also will be, or the contribution will be to design also a 3D cooling system for reducing the temperature, the thermal that is producing at the MOSFETs and the transformer. Um, Uh, from the requirement, as you see here in the table, we are before we start designing and simulating our dual active bridge using SIMBA, we get the information from the requirements and from the system engineer that the input voltage and output voltage shall be in the range of 600 to 850 and 120 to 450 volt, and the indexes, the stray indexes is 5 microhenry, ratio transformer 0.45, and switching frequency 100. And by the way, we can also run to 200 also kilohertz. And the capacitance on the input and voltage output 40 microfarad. And you can see on the right side that the simple dual active bridge circuit consists of on the right side the primary H bridge, and the secondary side the secondary H bridge, where we are providing a signal, the WM signal to switch 1 and to switch 2, switch 4 and 6, and switch 1 and switch 4 are diagonal with the same signal, 2 and 3 diagonal with the same signal, also applicable for the primary side in a single phase shift. Just the signal on switch 5 has been shifted with the phase shift from 0 to 90. Depends on your power flow. If you would like maximum power flow, you can apply 90-degree on the switch 5 or in the secondary side with respect to the primary side. But for our application, because we would like to run with a high efficiency over than 98%, so we decided to go in a triple phase shift, where we are applying phase shift in the primary side between switch 2 and 1 with different some defined phase shift, which is going to be defined from the triple phase shift optimizer, and another phase shift on the primary side on switch 6 with respect to switch 5, and of course the main phase shift between the primary and secondary, which introduce the power flowing from the right to the left, or from positive to negative. As you can see here, you have the shape of the voltage on the primary and secondary side if you apply a triple phase shift. And as I said, if you apply a positive phase shift from 0 to 90, you will get direction. For example, it depends on your definition, direction from VP to VS, from primary to secondary. And if you apply phase shift negative, you get a different direction. So the phase shift between the primary and secondary decided how much power is flowing from the primary to the secondary, and vice versa, where the phase shift on the primary side and secondary side with respect to its to the near or to neighborhood switch reducing or optimizing the switches in such a way that the losses can be reduced and you increase the efficiency. This is the model, the double active bridge model that we are using. Of course, we are now using ideal transformer. In the new work, we are using the real transformer where we get too many issues like a parasitic effect. This model consists of the voltage and the current controller in a cascade mode. Of course, you can use it as your requirements. Either if you would like to control the power, you can use just current controller. If you would like to control the voltage, you can use voltage with the current controller. And this voltage and current controller is controlling the phase shift between the primary and secondary. If we call it D2 or D3 or Phi3, and the optimizer, which is written in C code, is going to calculate the other phases in the primary and secondary side to optimize the device and reduce the losses. Thermal model has been also added in the beginning to evaluate the conducting and switching losses and to see how much losses we are getting. Of course, using this thermal model needs some information from the MOSFET devices, like an .xml file for the MOSFETs switches, and this has been added and evaluated. We have the high frequency transformer with the 100 kilohertz till 200 kilohertz with transformer ratio of 0.45. In reality, it can be adjusted. And the primary high H bridge and secondary H bridge. As I said, we started with the single phase shift, and then according to the requirement, we say no, we cannot get. Of course, in practical or in theory, you cannot get high efficiency with over than 90-80% if we use single phase shift. For that, triple phase shift was the purpose to increase the efficiency and reduce the losses. And as you can see here, we start working with the triple phase shift optimizer. First of all, was offline by assuming that the phi 1 and phi 3 are equal, and we have to use some optimizer such a way that we can keep the power, the level constant to each constant, and we should not lose the introduced power. And for that, you can see that by using this optimizer, we can reduce the I current in the inductor, or the peak current, from around 160 to 130 in one of the best cases, such a way that we are not loses the introduced power or the command power. Under different operation point offline, we create a lookup table with the different input and output voltage. As you saw before in the input voltage and output voltage, we are going to work in a different range. And for that, we create a lookup table from the previous evaluation, which was also based on a SWIP. SWIP has a SWIP script from Python in our model, and we create a lookup table, and from a lookup table we could also generate the best fitted surface that we can work on this surface to get the optimal phase shift value on phi 1 here and phi 2, and sometimes you will say D1 and D3 or D2, but this is phi 1 and phi 2 means phi 1 is the primary side, phi 2 is the secondary side. Other one was to work with online triple phase optimizer. Of course, there is different optimizer for the triple phase shift, using Lagrange multiplier method, using IE, using swarm, practical swarm method, a different method. This constraint optimizer that we use it is the Lagrange multiplier method because it's very easy to implement and doesn't need too much computing time. And for that, Lagrange optimizer method is just finding the optimal solution, or depends on your your object function. For example, in our function, the object is to reduce the I current, the I peak current. Sometimes some of the engineer or the developer, they reduce the RMS current. For our case, we are reducing the peak current, and under the constraint of the power, that such a way that the power shall not be shall keep constant. And for that, you have to define your object function, which is the I current in the inductor, as a function of D1 and D2, which is the output from the optimizer, and also D3, which is the phase shift coming from the controller. And with the K, which is the voltage, the voltage in the secondary side divided by primary side. And for that, you have to collect also to get the constraint function. You have to define it, which is in our case the power as a function of D1, D2, D3, and formulate the Lagrangian formula, which by adding the Lagrangian multiplier lambda, and then just take a partial derivative for all of this function, for all of these equations, and in the end you will get D1 and D2 as a function of D3 and key. And you can see this is one of the operation mode. Of course, a different operation mode has been studied from operation from mode 1 to mode 6 for one direction, and 1 star to 6 star for the reverse direction. And this is just one example where the I pick is a function of D1 and D2, which is D1 plus K D2, and the power is 2K multiplied by D1 D2. And in the end, if you apply the Lagrangian using any tools, either so you can solve it manually or using Python script or MATLAB, you can find the D1 and D2, or the phase shift, as a function of D3 and K, and then apply this phase shift to your model. You can see here what is the effect of the optimizer. If we work without optimizer, you see in the left side, the high frequency current is around 205 amp if I run without optimizer. But if I apply the online optimizer, you can see that I could reduce the current from 205 to 142 with around 30% current reduction. So we could reduce in the best cases 30% current reduction. You can see here the conducting losses evaluation in closed loop controller. This is one example that I told you where the conducting losses has been evaluated between all of the switches. Here I saw just one example on the S5, which has the most efficient current that's flowing through this switches, because it's responsible for the phase shift between primary and secondary side. And without an optimizer, you see that the conducting losses is around 1 kilowatt, more than 1 kilowatt, is around 1 kilowatt. But if I use an optimizer, I see that, or we can see that, conclude that we are reducing the conducting losses to around 400 in steady state, 400 watt, from 1 kilo to 400. So 600 watt has been reduced with around 60% losses reduction at the best cases. So by using the optimizer from a Lagrange optimizer in some operation mode, we could reduce power losses with the 60%. With that, if you see here on the right, on the right side, the efficiency versus the voltage. If we don't use the optimizer, without optimizer, we could just in some of the operation mode from 150 to 120, we just go to around 90% efficiency, and from 200 to 350, we are between 96 to around 90, and get also reduced with a higher power. But if we use our optimizer, we can see that we are getting to go over 98% in a wide range. of operation mode of operation point from 180 to 450 in circa 98%. And that means we could get uh, efficiency equal to or over the 98% over a wide range of operating condition if we use the Lagrange multiplier optimizer or the offline optimizer. In the end, we combine the offline optimizer and an LMM optimizer together to work in the whole range from zero to low power, and from low power to medium power, and from high power to and over the high power. All of this offline and online optimizer has been merged to work in this three section of power to work together, because you cannot we could not use the LMM in the whole range of power. So we decided to take just two moves from Lagrange optimizer to work in medium power and high power, and at low power we use the offline optimizer.
I'm sorry to interrupt, Khaled, but you have basically 1 or 2 minutes left. So
Yep.
sorry about that.
No problem. I'm finished. Thank you for your your time. I appreciate the opportunity to speak with you today, and I'm ready to answer your question if there is. And if you need any information, feel free to contact me on this email. You can send me any message anytime.